Good evening, everybody. Okay, we'll see if a lot of what Pat discussed and some of what Dr. Myers talked about, I'll be covering also, maybe from hopefully a little different perspective. I call it the engineer's perspective, probably the practitioner's perspective might be even a better way of saying that. My company, the Mannik and Smith Group, has now designed 4 GFRP bridges. Pat touched on several of those. There's one additional one, a fairly large one that we'll touch on also, that are going out to bid. Pretty interesting material. Mannik and Smith first got involved with this a couple of years ago when approached by Owens Corning to help do an independent cost study on GFRP and bridge deck design, and wanted to get an idea what's the reality there. And they knew their material costs and that, but what's it actually cost to construct a bridge, the labor costs, the delivery costs, all the things that go into constructing a bridge. So we're going to, this is actually typically an hour presentation that I've chopped down to 15 minutes, so there may be a lot of questions, may not be, but I did my best to cover what I think are the important things here. So we've already touched on it. In 2009 was the first design spec. The Anthony Wayne Trail Bridge that Pat referred to was designed with the 2009 specification. The other 3 bridges that we have subsequently designed are with the new second edition that came out the end of 2018. And there's been the AASHTO LRFD bridge design specifications also been updated to align with the GFRP design specification. And when we design bridges for the Ohio Department of Transportation, we have to do those in accordance with the ODOT bridge design manuals, which are from 2004 and 2007, so they're a little bit older. So we're taking new, old, and as practitioners trying to put that together in a way that meets all the requirements of the government and the industry, and at the same time trying to be as efficient as we can be as engineers in the design, especially using a new technology. Some of the things that the difference between the 2009 and 2018 specifications really were in the area of compression, torsion, and substructures. In the 2018 edition, they expanded the original 2009 to allow us to design in different regimes and different parts of a bridge. 2009 we're really just kind of focused on the design of the superstructure itself. So in the 2018 edition, we've been able to go beyond that, which is a very good thing. We've talked a little bit about it, but some of the major differences between the mild steel, epoxy coated, and GFRP, strain compatibility, limits of reinforcement, control of cracking, we'll talk a little bit about that, shear design especially, mechanical connectors, and the barrier systems. When I say barrier systems, what's happening, for instance, with most DOTs, and the Ohio DOT in particular, we cannot, the Anthony Wayne Trail Bridge you saw, if you look close at the pictures there, the barriers are designed with epoxy coated reinforcing steel while the deck is designed with GFRP. Why is that? Well, there's been no testing, crash testing, on barriers that would meet the ODOT design criteria. Texas DOT, they have, Florida DOT has, but Ohio DOT has not. And because we don't have a national standard, and this is something as a practitioner we really wish we had in the country, a national standard for barrier design, that forces all 50 state DOTs to come up with their own designs. So we've got a lot of differences there, and it has resulted in Ohio that we've up to now not been able to design the bridge barriers with GFRP material. That is changing, by the way, so that's a good thing. In the bridge deck design, control of cracking, what we find is that the major differences between designing with GFRP and mild carbon steel is that with mild carbon steel, as Dr. Myers mentioned, you don't have a yield point. You have a linear transition up to failure. What that does, in essence, is forces the design of concrete bridge decks to be really more about serviceability and shear versus with epoxy-coated resteel, it's really about your strength states, limit states. So we have a different design regimen that we're dealing with, and as practitioners in bridge design, it requires you to think differently and to look at bridge design differently. What we're hoping, though, is that over time, the design regimen of going of really focused on crack control in bridge decks, and that's really what's driving up the, and we'll take a look at it, the amount of reinforcing going in bridge decks. If we can transition, continue to improve our design specifications with the research that's going on, the C sub E factor is a great example there. We're at 30%. Research is showing maybe 12, 13%. Maybe we can save on there. So research is really important, and the material itself. Pat mentioned it, I think, the low modulus of elasticity. If we can, the industry can continue to improve on that, all of a sudden now, instead of designing for crack width and shear, we're going to start now be designing more in line with the way we do bridge deck design, which is more in first tensile design of a reinforced concrete beam, basically. So that's where we're hoping to eventually get to. And you can see the crack width limit right now, which is better than it was in the 2009 edition, is in 2018 edition, is set at 0.028 inches, less than a 32nd of an inch. So it's a pretty tight crack, and yet it still requires, even with that, a lot of reinforcing, a lot more than we'd like to see, certainly not for strength. Shear design, because of the anesiotropic nature of the GFRP, it's weak in shear, where we typically wouldn't even worry about shear. In the design of concrete bridge decks, yeah, it's one of the controlling characteristics that we have to work around, unfortunately. In the design of bridge decks also, what's really important from a practitioner standpoint, we do a lot of part width construction. So we're taking existing old bridges and putting new decks on them, widening them out. And to do that, we typically have to maintain traffic. And to do that, we take out a portion of the deck and replace that. And then we build another adjacent portion of the deck and replace that and move traffic back and forth. And to link the two sections together, we have to take our bars and connect them somehow. And typically, we don't have enough space to do laps, so we end up using mechanical connectors. Right now, the projects that we're bidding out that have been built, and as Pat said, are being bid out, will use probably galvanized steel mechanical connectors. Where we really want to get to is we want to get rid of all metal in the bridge deck, and what we're working on right now, Owens Corning is working on, are GFRP mechanical connectors. At that point, now we've taken all the steel out of the bridge deck, and that will give us our most efficient and long-lasting deck. Again, and we're hoping to do the same thing in the design of the barriers. Now, I'm going to quickly go through, Pat touched on these, but I'm going to quickly touch on them again. The Anthony Wayne Trail Bridge, there's a little graphic here which shows where it's at in the city of Toledo, right at kind of the heart of the entrance into the city of Toledo. Going over, this is what the, you can see the rail traffic going under that bridge while it's being constructed, and that's what Pat was alluding to. Very difficult conditions to work under. One of the things, the attractions, we thought initially with the GFRP was that in doing some prototypes and mock-ups with full-size mock-ups with contractors, we found that these were going to be erected in about half the time. We thought, man, that's great for this project because we want to get in and out as fast as we can. Well, the doggone railroad didn't want to cooperate on that, so we didn't actually save time, but it wasn't because of the GFRP at all. There's just a quick cross-section of the bridge itself. And here's a comparison. So we've got epoxy-coated resteel. You can see, I won't read all of it to you. You can see the differences. And again, remember, this is on the first edition, the 2009 GFRP, when we designed this. So this is a little less efficient than what we're designing right now. And you can see the percent volume change in the designs, anywhere from 28% to 53% more GFRP. Yet at this, and why was that? It was because of the crack control. It wasn't about strength, it was about crack control. And when we compared to the first edition and second edition, again, we didn't build it with the second edition. It had already gone out for construction. But for our own curiosity as practitioners, we went back and we said, okay, what's the impact? What's the difference? And we see, and again, it was crack control governing the designs, but on average, you went down roughly about 9–10% on the volume of reinforcing that went into the deck, at least on the Anthony Wayne Trail Bridge. Here's another one, Industrial Drive Bridge in Northwest Ohio. This is a large bridge designed initially using epoxy-coated resteel. It's for a county engineer in Henry County. Goes over the Maumee River, a very large river, not quite the size of the Ohio River, but it's pretty good size. That gives you a little bit of an idea looking from an aerial. The bridge is it's got 8 spans. It's almost a 1,000-foot long bridge, so it's a pretty substantial bridge. We were approached by the county engineer after he'd heard about what ODOT was doing about redesigning the superstructure using GFRP. Now this one we were able to use the second edition of the AASHTO specification, and you can see the difference between the epoxy and the GFRP. It's fairly significant in the volumes that we had there, anywhere from 33 to 75% more. Doran Hill, this one again Pat was talking about, that just went out to bid. We have not seen the cost numbers yet on the bids, but and we'll take a look here at our estimates, and I'll be very interested in see how the estimates came in. Again, just a aerial view of the bridges on Doran. This one's on Hill, and quickly again just profile views of the bridge. And again, very similar results there, 27 to 50% increase in material. Again, it was mainly shear and crack control that's governing the designs. So you're looking at it and you're going, man, that can't be a good story there. This got to be costing a fortune. Well, what we found on the Anthony Wayne Trail Bridge, now this again was with the 2009 specification. With epoxy, it was working out to $8.05 per square foot. Using the first edition GFRP, it was at $9.59 and $8.76 in the second edition. Now, what we're starting to find now on industrial drive, so what happened in the meantime is steel prices have been increasing. Part of it's driven by the Chinese, and part of it's just a lot of it has to do with a heavy increase in construction in the transportation industry driving up the price of steel. So recently in the last year it's gone up 15 to 20%, which has driven the cost of epoxy coated reinforcing steel from $1 per pound to roughly $1.15 per pound. And now we're starting to see that the costs are starting to come in closer and closer. Now, on the industrial drive project, the one over the Maumee River, we're estimating $11.81 per square foot and GFRP at $10.61. and Doran Hill. Now this one's interesting because this is some of our latest costing information. This is the project that just got bid out. Our estimates on that are 1014 or 1010 on epoxy, but 1002 with GFRP with mechanical connectors, and it drove all the way down to $8.56 without mechanical connectors. So what we're seeing, even with those large volume increases, and I do think that with future editions of the AASHTO design spec, we're going to see that come down. But we're already seeing now that the GFRP on a first cost basis is now less than the epoxy coated resteel. This is, I put this in here, it's about a, I'm not sure, hopefully it'll, if we can hear him. Yeah, we're not hearing him. Okay, I'll tell you what. This is a, I'll speak for him, I guess, real quick. This is the superintendent for Miller Brothers Construction. They're the ones that built the Anthony Wayne Trail Bridge. It's unfortunate we can't hear him. But what he's talking about is their first experience with GFRP rebars on that bridge and what they found as they built the bridge. And of course, we saw the ease of construction. It was built, the reinforcing is able to be installed at roughly half the time as conventional steel. And it was safer for them. The bars themselves tend to have a frictional coating on them. Glass, real fine glass coating, so they can walk on them. Epoxy coated resteel, when it gets wet, damp in the morning especially, with dew, people are slipping and they get hurt a lot. And then the lightweightness of it, it's really important because they're having trouble getting young people going into the construction trades now. And part of it is when you have to carry heavy loads, you know, on your shoulders day after day, it breaks you down physically. And you're seeing guys retiring before they're 50 years old. All of a sudden now, Ben's telling us that these guys like the work, they enjoy the work, everybody, these kind of guys like to do the construction, and they see this as lengthening their careers, this type of a product. So conclusions here. A lot of it we've already gone through. But one of the keys on this thing, again, I just want to get down to it at the very bottom, is increasing the modulus of elasticity. Right now it's about 1/4 to 1/5 that of steel. If we can get that, improve that just modestly, and we can then go from shear and crack control design to typical strength control design, all of a sudden we have completely changed the cost dynamics of design in bridges. And I really think that this harkens back to the early 70s when epoxy coated reinforcing steel first came on the scene. People were thinking, I'm not going to pay all that extra money for epoxy coated resteel. That's crazy, you know. We don't do stuff like that. Well, slowly over time, and it was really driven by the owners, so the state DOTs, county engineers, people that are building, that are going, we got to have something that'll last longer. So you ended up building with that. Even though it ended up costing more, you ended up building with it. And today it would be considered heresy, if you design bridges without epoxy coated resteel and you just put in mild uncoated reinforcing steel. So at that time you had a paradigm shift in how bridges are designed. I think we're on the verge of the same thing with FRP products. And as you saw, the first cost now is at or below mild reinforcing. And the research that's coming out, there was a paper, I think Dr. Nani was one of the co-authors on it, pointed out that with the new research that's come out on durability, that 100-year plus bridge decks are doable. You can't get that with epoxy coated reinforcing steel bridge decks. So if you can win on first cost and life cycle cost, I think this is going to be what they call the proverbial no-brainer. So with that, I'll just kind of leave that up there, but as I've covered all of this, I think that was the end of it.
Thank
So-
you very much, Richard. Don't delay. If you want to take a seat.